Yeah, thank you, Crystal. My name is Tobias Stollenberg. I work at the German Aerospace Center in Cologne, and this work was done in close collaboration with people from NASA Ames, where I was the last 3 months. The problem I'm talking about today is a special problem from aerospace research, which is the deconflicting of wind optimal trajectories. Here you can see that there are, every day, there are around 1,000 flights across the Atlantic, and right now flights are routed through like aerospace highways, but people are thinking about doing something called free flight trajectories to fit more flights into the limited airspace. And then you get something called wind optimal trajectories, which means fuel-saving trajectories. But of course there will be conflicts. You have 1,000 flights, and if you calculate these wind optimal trajectories, there will be conflicts. And the problem is how to avoid these conflicts. And classically, this is done, for example, by deviating the trajectories globally. And this is the work we used as a starting point. So this is the classical algorithm. They use simulated annealing to change the trajectories and avoid the conflicts in this way. But we want to map this problem to solve it on a D-wave machine. So, and as Crystal already told you, this means we want to formulate the problem as a QUBO or an Ising model. And I'm going to tell you about that in the next slides. So, first of all, let's try to formulate our optimization problem. The easiest thing to do is to consider the following means to avoid the conflict. The easiest way is to just keep the flight on the ground for a certain time. So these are the departure delays. I can keep the flight I for a certain amount of time on the ground. And of course we want to keep these delays as minimal as possible. Therefore the total cost function is giving as the sum over all these departure delays over all flights I. And but at the same time I want to avoid all the conflicts. This is my optimization problem. Of course, this is the easiest approximation. You could also think about maneuvers, and we already also did that, but I will start with this easy model because it's the D-wave machine has limited qubits, and it just makes sense to start with an easier problem. So the first simplifications we are doing, we are only considering pairwise conflicts. So if you have a conflict like that with 3 flights, we consider them as 3 different pairwise conflicts, which is just a reformulation of the problem. And now we have to look at the possible conflicts. So you can imagine you have 2 trajectories of 2 flights intersecting each other. But if they are really in conflict, depends on the arrival time of these 2 flights. And this delta k here is the difference in the arrival times of these 2 flights. Of course, it depends on the delays of both of the flights. And the tik is the arrival time at the conflict in the wind optimal case. And if this difference in the arrival time is very small, then there is no conflict. And if it's very large, there is also no conflict. But if it's close to 0, there will be a conflict. So we are saying the conflict is a real conflict if this difference in the arrival time is smaller than 3 minutes. But what we have is the conflicts, they come in clusters. So this often looks like that. You have like a parallel conflict. So one flight is going like this and the other one is going like this. And if you want to avoid these conflicts, you have to fulfill this relation for all the pairs of the trajectory points here. And this leads us to constraints to avoid conflicts. which is the difference in the departure delays must not be in a certain interval, which is given by the arrival times of the flights at the conflict. So this is what you have to imagine. The difference in the arrival times, the difference in the departure delays must not be in some interval to avoid the conflict. And then we can write down our optimization problem as we minimize the total delay with a constraint that this difference in the departure delays is not in this interval. And we do this for all the flights I and all the conflicts K. And if we solve that problem, we have a solution which minimizes our cost function, the total delay, but at the same time avoiding all the conflicts. So how does our problem look like? So first of all, we can subdivide the problem, which is a good thing because we want to put some small testing problems onto the D-Wave machine. So as you can see here, the green flights and the red flights, they are not in conflict with each other. You can also write that down as a graph. So each of the nodes in the graph is a flight and each of the edges is a conflict. So these green flights here can be represented as this graph, and this is one small sub-problem we can study, and the red trajectories are an example for a little bigger instance, which looks like that in the graph representation. And in total, if we assume a maximum delay for all, a maximum departure delay of 18 minutes, we get like 50 of these sub-problems. And of course, there are, these sub-problems look like this. So here you can see the number of these sub-problems against the size for different maximum delays. And you can see that there are a lot of small problems. For example, for what we are using, oh, it's not displayed here. So we have a lot of problems where we only have 2 flights with 1 conflict, and at the other edge of the graph, you can see that there are a few very big clusters of problems. And these actually don't fit on the machine, but we can use all these small sub-problems to test our approach on the D-Wave machine. Okay, so the next thing we have to do is to discretize our problem, because the original optimization problem had continuous variables. But in order to map that to a cubo, we need to discretize our problem, and we do this equidistantly, like this. So the departure delays will be separate, discretized in this manner with a certain step size delta d, and the maximum departure delay. And here you can see on the left side the result of an exact solver. So we solved this optimization problem with the classical computer. And here you can see the cost function, and on the horizontal axis you can see the discretization step size. So if we have a fine discretization, we have an optimal solution, but if we have coarse discretization, the solution quality decreases. So what we want to do is have a very fine discretization, actually the one with step size 1 minute. This is the scale in minutes. Okay, and now we can map the problem to a cubo, and this is done in the following way. So right now we have integer variables, right? So we need to map these integer variables to binary variables, and we do this with the so-called one-hot encoding. So the departure delay, di, is written as the sum over binary variables di alpha, and the alpha is now can take all the values the di can take, and of course if we do that, we have to make sure that for a given I, only one of these alphas is actually 1 and all the others are 0. And this we do in the following way. So now we can write down the cost function as a cubo. So the first term of the cost function is just the sum over all departure delays. So this is the sum over di over sum over I over di with some factor. So this is our original cost function, and the constraints we incorporate by two additional terms. So the first term is due to the encoding. As I said, only one of these alphas can be 1 for each flight, and this is ensured by this term. So if this is the case, then this term is 0, because here I sum over all the alphas, and if only one of these di alphas is 1, I get a 0 here, and if this is not the case, I get something else here. And because I want to minimize the whole thing, yeah, the constraint is fulfilled is this if the contribution is 0 here. And the same holds true for the third term, which is due to the conflict avoidance. So I sum over all the difference in the departure delays, which are inside this forbidden interval, and if the 2 bits are activated, then this is penalized. So then the cost function increases, and we don't want that. If we get the ground state of this, then this will not happen. And of course, we have to put some sufficient penalty weights in front of these 2 terms in order to make sure that the ground state really fulfills these constraints, so that the contribution to these 2 terms is 0. And in order to find the minimal sufficient penalty weights, we again used an exact solver on a classical computer to solve this cubo, and the result can be seen here for some of the instances. So this this axis is the 1 penalty weight, and this is the other penalty weight, and the green dots are valid solutions, so where the contributions, the constraint contributions vanish, and the red dots are the cases where the constraint contributions do not vanish, so the constraints are not fulfilled. And you can see that you have something like a box here, so you have to make sure to keep your penalty weights above these black boundary here. So, and then we come to the quantum annealing. So we embedded these problems into 2 of the D-Wave machines, the D-Wave 2X and the D-Wave 2000Q, and we could embed up to instances with flights, with 64 flights and 261 conflicts. I will skip over this due to the time. So, and then if we embed the problem onto this chimera graph, we can solve it, and there are some parameters we tried out. The first one is the coupling in between physical qubits which belong to one logical qubit, and we changed the number of annealing ones, and we also used gauging, which is we call this gauging, which means we flip the spins randomly yeah, this is just a method to get out offsets. So, and this is one of the results. So this is the time to solution. We calculate the time to solution with 99% probability in this way, where P is the success probability. So you run the problem like 10,000 times, and if it finds the exact solution 100 times, you get a certain success probability. And if you plug that in here, you can calculate a time to solution with 99% probability. and this t is the annealing time, which is like, we always use 20 microseconds. And here is the result for, this is the time to solution against the number of flights. And the three different curves are, the colors mean, the red color means a very fine discretization, which we need actually to get good quality solution, and green is more coarse, and blue is a coarse discretization. And the dashed line is the 2000Q, and the solid line is the small machine D2X. And you can see that the time to solution decreases for finer discretization and also for bigger problems. So on the horizontal axis there's the number of flights, or here it's the same data for the number of conflicts. So for bigger problems the time to solution increases because the success probability decreases. And we found that this is due to the limited precision of the machine. So to investigate that, we looked at first of all, we wanted to get rid of this parameter of coupling in between the physical qubits. So we varied this parameter and always found a maximum, which was problem dependent, and then we looked at this is the success probability against this coupling, and here we have this maximum success probability with an optimal JF coupling against a certain number, which is a measure for the precision needed on the machine. And you can see that if the precision needed is about 30, or in other words 1/30, which is roughly the precision of the machine, then the success probability declines here. So this is the reason for the slide I showed for this behavior here. Of course, we haven't investigated different annealing approaches, different embedding approaches. We just used the embedding algorithm from the D-Wave RP, but there are also some smarter things one could think of. Yeah, but this is what we found by using the default method. Okay, yeah, I think I will skip this slides. So as I said in the beginning, you could also include maneuver delays. So if you can think of avoiding conflicts in the air, and this is of course what is more realistic, and we can actually map this problem also to QUBO, but we haven't done any annealing runs on that so far. So I will skip over these two slides and come to the conclusion. So I showed you that we can map this deconflicting of wind optimal trajectories to a QUBO. And we found that one needs fine discretization to solve that problem. We found annealing solutions with the D-Wave machine for small instances. And the next steps could be to reduce the needed precision by alternative embedding approaches and solve the maneuver model on the D-Wave machine.